today we are going to discuss something else. It is not spin. Okay, so something else, and this is known as what is known as perturbation theory. Of course, in the context of quantum mechanics. So how many of you heard about it, this perturbation theory? And what is the need? What is this theory? Any idea? Anyone is having any idea? What is this perturbation theory? Maybe some of you would
I
know.
think it's for the
For the
sir,
what?
I think it's used for the deviation from the real picture.
What is that? So the point is as follows. Although we know what the equation to solve, so this time independent Schrodinger equation, but this time independent Schrodinger equation or the eigenvalue equation, it cannot be solved for most of the system. So this can be solved exactly for only few cases. What are these? What are the examples where you can solve this exactly? You already know. Give me an
Particle
example.
in box,
Okay, particle in a box, you know. But
hydrogen
for
atom.
hydrogen atom is better because particle in a box is a model problem. No, hydrogen atom is a real problem. Of course, you can, if you want, you can put particle in a box. Of course, harmonic oscillator you can solve exactly. What about anything else? You know, rigid rotor, which this can also be solved exactly. What else? What else? Make particle in a box. Okay. So hydrogen atom, harmonic oscillator, rigid rotor, particle in a box. Okay, these are examples where you can solve exactly. But if I go to a system like, for example, helium atom or any molecule, cannot be solved exactly, isn't it? Then what do you do? Of course, you can solve it on a computer. Using a computer numerically. But this is called numerical solution. And you'll see that many groups across the world, they use computers to solve problems in quantum mechanics, chemical problems. Okay, but they use some software package or sometimes they write their own codes, but these are solved numerically, not analytically. But today, the what I'm going to talk today is known as perturbation theory. So let us start with an example. I can have a particle in a box problem. 0 to A, the particle is confined inside a box of 0 to A, and you know that at the boundaries potential is infinite. At the boundaries, inside it is 0. I don't know whether it is discussed, but one good example of particle in a box problem, qualitatively good example, is what is known as the conjugated polyenes. How many of you know conjugated polyenes? It is something like this. Like this. Okay. So I can think this is a conjugated polyene. So at the boundaries, potential is very large. Inside it is 0. So this is one crude way of actually modeling this electron, these pi electrons in this conjugated polyene. Has it been discussed in the context of particle in a box?
Yes,
Yes,
sir.
sir.
Okay, so you know. Now I ask one of my colleagues who is very good in synthetic chemistry, some organic chemist, and they can do something like this. They can, for example, they can replace one of the carbons with nitrogen. What do you expect then? If you replace one of the carbon with nitrogen, what do you expect? And then I ask you to draw the potential energy for this system. What will be your answer? What will be your answer?
So the potential energy is not constant now, I think.
Yeah, what is happened? There is a replacement of one of the carbon atoms by one nitrogen atom, which basically means the potential around this nitrogen atom would be different. Now, nitrogen atom, you know from your school chemistry that it has more electronegativity, isn't it? It is more electronegative. It will pull electron more towards it, isn't it? So one would expect that there will be small change in potential as you go along around this nitrogen atom. There will be a dip in the potential. So it will no longer be particle in a box, perfect box. There will be a dip around the nitrogen atom. So there is small change in the potential. Small change. And this small change is very small compared to the potential itself, because you have changed only one atom. And this small change could be viewed as what is known as perturbation. Okay, so I'll give you, we will discuss this, we'll come back and discuss it later, maybe today or not, if not today, then Friday. Okay, so another example let us give you another example. So if you have this is a nucleus, and then you have an electron. Of course, this is not the picture. It is all over the place, no? Quantum mechanically, you have probability of finding the electron. For hydrogen atom, you remember what is the ground state energy of hydrogen atom? You remember the number?
13.6.
Minus 13.6 electron volt.
13.6. Okay, yeah, something like that. This is the ground state energy of hydrogen atom. Now, if I pull this, if I take the electron, say if I have an electron, say around 10 angstrom, little far, 10 angstrom from the nucleus, then what is the electric field? Electron is 10 angstrom away. Sorry, from the nucleus. What is the electric field at that point? Electric
Not
field?
by R.
Yes. Electric field, can you tell me roughly the electric field is?
E not divided by distance.
Yeah, something like 13.6 divided by this is electron volt, and divided by this 10 angstrom is how much in meter?
10 raised to power minus 9 meters.
This is roughly, can anyone tell me, say if I assume this is to be 10, then what is this? This is roughly, of course, you have a factor of 1 point something, but it will be something like 10 to the power of plus 10. What is the unit? Volt per meter, isn't it? This is electric field experienced by the electron, which is 10 angstrom away from the nucleus. Okay, is it okay? So the electron feels about 10 to the power 10 volt per meter field when it is away 10 angstrom from the nucleus. Okay, is this clear? Say yes. This is a very simple thing. 13.6 electron volt divided by the length, the distance rather.
Yes, sir.
And in a typical experiment, when people do experiment, sometimes they apply electric field from outside. In a typical experiment, let me write down. In a lab, electric field, you can bring an external electric field, applied or used, is about, say, I can tell you, give you the number, it is something like 100 volt per meter. Okay, so 100 volt per meter. So I take an electron, apply electric field in the z direction. So if I have the Hamiltonian is, I'm given by, say, age 0. This is unperturbed when there is no electric field, and then you apply an electric field. It is something like E minus E times some capital Z. This is external electric field. But what is important here? What is the point? What I want to manifest or emphasize here? The number, a ballpark number. The applied electric field is 10 to the power 8 times weaker than the electric field felt by the electron. So what do I conclude from here? So this is a perturbation, this minus E times Z, minus E times capital Ez. This perturbation is extremely weak. So this perturbation will change your Hamiltonian. Your total Hamiltonian will be something like this. Will be given by the Hamiltonian without the electric field plus this correction, which is minus E times Ez. This correction is negligibly small compared to the energy without the electric field. So as long as this is valid, and this is valid in most of the experiments, external electric field is much weaker, very weak. Then the formalism I'm going to discuss today will be applicable. Okay? And this is known as perturbation theory. So this minus E times Ez is your perturbation. So this perturbation is very weak, or perturbation is small. Okay. So how many of you had taken a course on this? Say people who are doing PhD 812, I think they had taken some course on perturbation theory in quantum mechanics, isn't it? Some of them at least. Please answer. Anyone from 812?
Yes, sir.
Okay, good. So let us do it now. So let us write down the Hamiltonian, and I say the Hamiltonian depends on some parameter, lambda, and this is given by H 0 within bracket. Basically means this is unperturbed Hamiltonian plus a correction due to perturbation, and that also that actually depends on some parameter lambda. Of course, this is small. This is very important. This equation I start. So lambda is a parameter okay, which will vary, and this is very important in this case. Now I go back to the original problem. Original problem is your hydrogen atom, for example, which is exactly solvable. You know the Hamiltonian H0, which is your exactly solvable. So H operating on psi will give you E times psi. Hydrogen atom or any other problem in chemistry, as long as you are doing with bound state problem, you have bound energy levels. Let's do it bound energy level. So
So,
yes,
so,
yes.
so what does this mean by H0 and H1, sir?
So I told you right now, no? H0 is the unperturbed Hamiltonian when
Okay.
there is no perturbation, and H is with perturbation, and H1 is the perturbation. Lambda times H1 is the perturbation.
Okay, sir.
Yes. So H0 is your Hamiltonian, which is exactly solvable. So for H0, you know all the, so we know all the eigenvalues, all the eigenfunctions and eigenvalues. So this H0 could be your Hamiltonian for the hydrogen atom, could be the Hamiltonian for your particle box, and that small tiny box is your perturbation in that case. Okay. So if I now ask you to write down this H0 operating on psi, what do you get? E times psi. But this is not complete. Why? Why it is not complete? Because I have to put something like n there. These are eigenstates, no? And this H, this psi is also special. Why? Because this is when there is no perturbation, no? So these psi 0 n are the eigenvalues, sorry, eigenfunctions. For example, it could be the eigenfunction of a hydrogen atom problem. If you are doing hydrogen atom problem, if you are doing particle box problem, these are the eigenfunctions of particle box. Is this clear? This you know. This is the unperturbed Hamiltonian. So let me write down again. This is unperturbed Hamiltonian. This is unperturbed Hamiltonian. Okay, is this clear? Now let us write down another equation, which is H. This H, of course, it depends on lambda, operates on psi n lambda. That will give you E n. It will also depend on lambda, of course, psi n lambda. So this is with the perturbation, the total Hamiltonian operating on your eigenfunctions. So what is the problem? Problem is as follows. So I have energy levels like this. These are like E1. Let us start from E0. This 0 means the ground state, huh? E0, 0. Of course, for putting in the box, you should have E1 here, but in general, it is the 0 level, 0 state. Then the next state, but the 0 within bracket means with unperturbed. Next one is E2, 0. The next one is E3, 0. You have all these things. So this is for the Hamiltonian H0. And you have corresponding eigenfunctions, of course. You have the eigenfunctions like this one is psi 3, 0. This is psi 2, 0. 0 within bracket means unperturbed. Now so these energy levels are going to change when you switch on the perturbation. When you switch on the perturbation, what is the perturbation? Perturbation is lambda times H1. So this will change. I don't know. It will go something like this. This is arbitrarily I'm writing. They are changing. What are these? This is the eigenvalues, but this I don't know. I'm just writing formally. This is for the total Hamiltonian, which is H1. What are these eigenvalues? Can anyone tell me? Actually, it is written here. This will be, this is E0.
Lambda.
This is also given lambda, but this is like this. This is E1, also lambda, like this, no?
Sir, it should not be H1, right?
It
Yes,
should
sir.
be H, sorry, like a lambda H1 plus H. A0,
Yes, sir.
yes,
A0
yes.
plus
Yes.
Total H, yeah. This is H lambda. Yeah, good. H lambda. So like this. Okay. So I don't know these energy levels. We'll see how to do it. So the one way to do it is as follows: that you assume that for the nth state, which depends on lambda, I am writing it as like this. For example, when lambda is 0, it should be, what is the value for this? This is for lambda 0. Lambda 0 means what? No perturbation, no? If I put lambda 0 here. And then you can have other terms which will be proportional to. These are the first order correction. This is called first order correction, which is lambda times something like En with 1 in the bracket. This is called the first order correction to energy. This term. What is the next term? Can anyone tell me?
Lambda
This is
square.
lambda square.
This is lambda square En for the nth energy state 2, and you have other things. This is like Taylor expansion. You can see, you know that if you have a function of lambda, what do? You write like f of 0 plus, what do? Lambda times f prime means first derivative of f with respect to lambda at lambda equal to 0 plus lambda square by 2 factorial f double prime lambda is equal to 0 taken lambda is equal to 0 plus higher correction. This Taylor expansion essentially is the same thing I am doing. So our motivation would be to find these corrections first, of course. Also, we'd like to know what are the corrections to the wave function. What will happen to the wave function? Similarly, the wave function with the perturbation is given by psi and lambda. When lambda is 0, what is this wave function? This is psi n, tell me, with 0 plus, now you can guess, lambda
Psi n1.
1 plus, so this term is first order correction to the wave function for the nth energy state. Okay.
Sir,
Yes.
sir, here psi n0 represent the wave function without any perturbation.
Yes.
So what does these two terms represent, like psi n1 and psi n2?
So this means these are the corrections. These are first order correction. These are second order correction. Because your wave function is going to change, you know. So wave function is written as a series. It is a zero unperturbed wave function plus corrections, and the corrections have corrections. The correction has several terms like first order correction, second order correction, third order correction, like nth order correction, like this. It is expected that as you go higher order in correction, the term will become increasingly small. The first order correction will have more contribution than the second order. Third order would have less contribution than the second order, like this. So these are the correction to the wave function. I can truncate it here. Then I'll have only the first order correction to the wave function. So what is the eigenvalue equation I want to solve? You remember what is the eigenvalue equation? H, total H, of course, which is a function of lambda, operating on psi in lambda, that gives you En lambda times psi n lambda. This is the equation you want to solve, but you cannot solve it exactly. And you're using this technique. You're saying there's a correction to the wave function, there are corrections to the eigenvalues. So I can substitute this. What is h lambda? You remember? This is h0 plus lambda h1.
H1.
It is like that, isn't it? What is psi n? Psi n is psi n0. So let us take only, only the first order correction. Let us do it, huh? That will be easier. If I take only the first order correction, then I have only one term, which is lambda psi n1. Okay, is it fine? Lambda psi n1. This will be equal to, En0 plus lambda En1 times, of course, En0 plus the En1. But if I take only the first order correction, but actually what should I do? Tell me.
Take all the values.
Take all the corrections, isn't it? And then maybe we will do something. So, but the actual problem is like this. Lambda square maybe this is fine. And any suggestion? What should I do now? Sorry.
Collect terms in order of lambda.
Yeah. So
Zero.
let us do. Yeah, we'll do that. Here I am taking all the term. Okay. I'm lazy. I'm not writing. So first, what you do is like a power series in lambda. What you have, isn't it? Now you have power series in lambda, and if I take lambda equal to 0, what is the answer for lambda equal to 0? The coefficients, of course.
H0 psi n0.
Perturbation 0, subnormal, everything.
Simple equation.
And this will give you what? This will give you h0 psi n0, and from the right hand side you'll get en0 psi n0, which you know exactly. This is an exactly solvable problem, isn't it? Which you can solve. Okay, this is fine. What about lambda equal to 1 coefficients? Can anyone tell me? There will be terms, no?
H0 psi 1.
Yes, it will be h0
H1.
h0 into here psi n1. Anything else? I think this is the only term from the
H1.
left hand side, no? This is the only term from left hand side.
No.
Psi n0.
Or you have one more
H1
time.
and psi n0.
Yes, because you'll have h1 and psi n0. Okay, so let us do it. Plus h1 psi n0 And also we'll have terms from the other side, no? Other side, what are the terms? From the right hand side?
En0 cyan 1 plus En1 cyan 0.
Yeah, see, this is 1. Be very careful, yes. En0, psi n1. So I can take it, I'll just take it to the other side. I can take it, no? So,
Sir,
yes, tell me.
so there should be one more term, right?
Which one?
H1 psi n1.
No, because that is lambda square. H1 psi n1 will lambda into lambda square. I'm talking about only lambda. Lambda to the
Okay.
power 1. Yes. Next term, when I compare lambda square coefficient, it will come. Okay, so from the right hand side, I'll get one term is En1 psi n0. What is the other term? En0
0 cyan 1.
psi n1. Okay, so both are negative. So it is En0 psi n1 minus En1 psi n0. Have you noticed something here? See, notice that lambda 0 means, see this, 0 plus 0 is what? 0, 0 plus 0 is 0. Lambda 1 means this, look at it. Can you see my cursor? 0 plus 1 is 1. Here also 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. So now you can guess lambda equal to 2. Sorry, not lambda equal to 2. Lambda square.
Sir, can you please repeat what you said?
Yeah, it is very
Your cursor was not visible to
not
me.
visible. Okay,
Hmm,
just wait. Just wait. Just give me. Okay. 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 Yeah, so what I'm saying that for lambda to the power 1 coefficient, lambda, so this is power is 1, lambda. So you'll see that all the terms, if you add these numbers within the bracket 0 and 1, it will be 1. 1 and 0.
Sir.
Yeah, the 0 and 1. Can you see the slide? You should be able to see the
Yes,
slide.
sir. Yes, sir. Now it's
Yeah.
clear.
0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. So what will be the next term?
Sir.
Yes.
Sir, I think the second term that is written, that is not only for lambda equals to 1, but I think that is for all values of lambda, this equation is valid. Right?
No. This is for lambda to the power 1.
Yeah, yes, sir. Yes, sir. Yes, sir.
Yes,
That's
yes,
what I'm
yes.
telling.
Yeah. Lambda to this is for lambda square. This is lambda to the power 0 actually. It's a typo.
Yes, sir. Yes, sir. Sir, another thing, sir. Sir, here for the Hamiltonian, I've taken the correction up to the first order, but in case of psi, I've taken up to nth order.
No.
So I think
That is fine. That is fine.
okay, sir.
That is fine because H1 I can take this, but this is you can make these things complicated. But let us take it that Hamiltonian is only first order correction, small correction. Other corrections are very small, but the corrections to wave function and eigenfunctions, even if you go beyond first order, they are not negligible. So that is the assumption. Of course, you can do more, like you can add H2 here and do this.
Okay, sir. Okay.
Problem with this eraser? Yes, just a minute. Yeah. So this is how. So what will be the
Just a minor
coefficient for?
point.
Yes.
The equation should be set to 0. The last equation written.
Yes. Sorry. If I now, what about the third this lambda square thing? Now you can tell. If I take
H1.
H0, What should I
Yeah.
take?
H1
Psi 2.
psi 1.
I should take psi n2. I don't even want to. And then what about the next one? If I take h1, then what should I take?
Psi n1.
Psi n1. If you had taken h2, you would have taken psi n0, isn't it? But I did not take in the perturbation. So what about the other terms? From the right hand side, you'll get how many terms?
I think 3 terms.
Yeah, so what are these terms? Minus, you can say en, if I take en0, obviously I will take,
Psi n2.
Psi n2.
okay, next thing is en1,
Psi
Psi
n1.
n Psi n1.
Psi n1.
and next one is en2.
Psi n0.
Yeah. So ideally I should have said this multiplied with lambda equal to 0, this multiplied lambda square equal to 0. So all the terms with lambda and lambda square and lambda cube, all these are separately 0. I'm just keeping all this and putting this to be 0. These are the coefficient. It's fine? Is it
Yes.
fine?
Yes.
Okay, and this is something which you can, which your exactly solvable problem, which you can solve exactly. No perturbation. What will be the next step? This equation I'll be needing. So I'll write it down again in the next slide. And let us write down. We write down h. This is for the lambda to the power 1. Psi n1 plus h1 psi n0 minus en0 psi n1 minus en1 psi n0. Sorry for the bad handwriting. Anyways, problem writing using this stylus. So this is fine. This is what you had from the previous slide. I just copied and pasted here. Is it fine?
Yes, sir.
Yes, sir.
Now what I am doing, I am just multiplying with psi n0 star and integrating. If I do that, what will be the first term? Some integration variable d tau psi n0 star h0 psi n1. What is the next term? Tell me. Is it
Psi
fine?
n0 star. Yes,
Yeah,
sir.
I think ideally you should also try to write it down on a piece of paper. ये क्या आएगा? What is the third term? Third term, good thing about that, this is number. No, n0 is a number, real number, eigenvalue. So I'll have d tau psi n0 star psi n1 minus en1 d tau psi n0 star psi n0. It's fine. I hope I have not done any typo here. I hope I have not done any typo.
Yes, sir. It's fine.
It's fine, no? Now, what about this term? The fourth term? Can anyone tell me what is this term?
It should be 1.
It is normalized 1. Okay. So let us now simplify things, and the way it is written in the thing, I'll write down. So d tau psi n0 star h0. Sorry for this handwriting, but I think you can follow. This guy, I put it here, this term first. This is fine. and I take this on the other side. En1 is, it is like En1, isn't it? Do I have any one more term should be there, no? This I taken, this I have taken. Okay, I have this term left, no? I'll take it on the other side. Hey, if I do any mistake, let me know, huh? Because if I don't write it on a big board, it's very difficult for me to follow. So I have written all the terms. All the terms I have written correctly.
Yes, yes, sir.
Now look at one of the terms very carefully. Say I take
Sir?
this term, which one? This one, listen. Yeah, tell me.
Sir, cyan 0 and cyan term that we have written, it should be 0 now.
Which one? No, 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 it will not
Cyan
be.
0 star.
No, 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 no. Because this is first order correction, this is a zero order. So they are not orthonormal. Had it been cyan 0 star and cyan 0, then it would be 0. There is no such relation.
Okay.
Okay, so these are the terms. Okay, now you recall, let us concentrate on this guy, the first integral. Let us concentrate on this. Actually, let me write it down again. One thing, this is 0 here, and star. It is not a function, like it's not a function of x, like that kind of 0. H 0 is here. This is the integral. Now you know that H0 is Hermitian. It's a Hamiltonian operator, no?
Yes, sir.
And you know the Hermitian property. What is Hermitian by definition? Since this is Hermitian, this one I can write it like as follows. You remember how to do it?
Zero into.
Yeah, let me do it. So I change the order of the wave function. I put it like this: cyan star 1 operating on this one. Cyan, sorry, 0 should be like this. And that is not the whole story. I have to take complex conjugate of the whole thing. This is the definition of Hermitian operator. Go and check your definition. Okay, this is fine. What is this? The next step. Now I can operate H0 on cyan 0. What should I get? If I operate
En0.
En0.
I'll get something like cyan star 1. Let me do it. En0 cyan 0. Obviously star. En0 is a number. I'll take a star of that, but that is it's not going to change because this is eigenvalue. Eigenvalue is real, isn't it? So I take this out. It will be En0. And then I have integral d tau cyan star 1 cyan 0, but I have to take a star of this. What is that? This is d tau cyan 1 . Are you convinced with this?
Sir, I have a question.
Yes.
In the first step that you wrote, where you took the complex conjugate of the
Yeah.
integral, that is just a property of the inner product, right? That is not property of the Hermitian operator.
See, this is one way to write actually. I prefer writing like this. So this is it is consistent with the definition of Hermitian operator. You see, if you read bracket notations like that, no, it has to be H has to be equal to H dagger, isn't it?
Yes.
See, it is exactly the same. You can go and check yourself. I prefer to write like this rather than how it is written usually in the book. This is exact. This is because it is easy to remember. We change the order of the wave function, okay, and then a complex conjugate of the whole integral.
Okay, sir.
They're same essentially. So what happens? This integral is exactly equal to what? another integral. What is that integral? This part. So this, look at it. This and the one I have written, are they same or different? They are same, isn't it?
Yes, sir.
Only the sign is
Sir,
different.
yes, sir.
So they will cancel. They will cancel. Convince? They cancel each
Yes,
other.
sir. Yes, sir. Yes, sir.
So then what will be the expression for En1? This is equal to, En1 is minus this is equal to 0. So En1 is equal to,
Sir,
yes, let me write down first. Yeah, tell me. Yes, someone was asking a question.
sir, in order for them to cancel, they should commute, right?
No, these are wave function. These are not operators. Operators commute. Wave function, they don't commute. Commutation is the relation of the operators, not the wave function. This is psi,
Okay.
wave function. Yes. Okay, so this is the expression what I have here. So what is this expression? Can anyone tell me what is this? If I multiply this with lambda, that will give me first order correction to energy. Of course, I could have used a bracket notation. If I had used bracket notation, what will be the expression? This will be psi n 0 h1 fine. So what I need to know, now hn you know, sorry, psi n you know, psi n 0, because this is unperturbed, the wave function or the eigenfunction for the unperturbed problem, and h1 is your perturbation, lambda times h1. So essentially you have to calculate this integral, and that will give you your correction to faster correction to energy. So if I have lambda here, lambda will come here. Sorry, my lambda. Give me a minute.
Sir,
Yes, tell me.
I want to confirm one thing. If we look at the at this expression, it seems it is the expectation value of the unperturbed state. So
It is the expectation value of
for
the
the
perturbation.
yeah.
Yes, you're right.
Okay, thank you.
Of course, but the expectation value is taken with respect to the unperturbed state.
Yeah, that is a energy correction to the perturbed state.
Yes. No, but I'm saying the expectation value is taken with respect to the unperturbed state. Your psi n is 0. Psi n is 0. Lambda h 1 cap. Okay. Now we have the expression for the first order correction to energy. So let me give you some example. Actually, it's always better to give some example. So since you guys like it and I also like it, party in a box problem. Remember, I had this. Between 0 and a. So and then I have a perturbation, and say I put the perturbation in such a way that the middle carbon atom has been replaced by a nitrogen atom. Then it will be at the middle perturbation. So it will be, of course, it's hand drawn like this. So basically your V of x Inside the box is what? 0 plus some correction. What is the correction? Some correction, no? Perturbation. What is the perturbation? Look at the second picture. This is, what is the midpoint?
V by A into X.
This is x equal to a by 2. And then I assume that the width of this box is very small. It is like 2 delta. So I can write it like this. Vx is equal to 0 plus or minus V naught. V naught is this height. Okay. So this is, of course, if this is when, if x is between what? This point and this point. What are these points? This is
A by 2 minus delta 2.
a by 2 minus a delta, and this is a by 2 plus delta. Delta is small. Okay, this is fine. And this is your perturbation, isn't it? This is your perturbation. Look at it carefully. Now, what is the ground state? Ground state correction to energy and to calculate. What is the ground state for particle in a box problem? What is the ground state?
2 by L sin
Actually, it is n equal to 1, no? It is psi 1, no? It should be root over 2 by A sine. Everybody knows this, no?
Yes, sir.
So what will be the ground correction to the, so the first order correction to the ground state? First order correction. Now ground state means here it is not 0, it is 1. This is, and if I multiply this first order correction to the ground first order correction to the ground state, okay? Now this is equal to, what will be the answer?
V naught plus.
Of course, you have to integrate from 0 to A, psi 1 star, which is a function of x. And then what should I put here inside the bracket? This is minus V naught, isn't it? This is the expression. Because it is V naught when it is between this, other is 0. So integral is actually from where to where? Actually integral is from a by 2 minus delta to a by 2 plus delta. And then if I take psi 1 star is equal to psi 1 because it's real. So it'll give you 2 by A, which is a constant, of course. You'll have sine square. You'll have minus V naught dx. Now I can do this integral, but I'm very lazy. What I'll assume the delta is so small that within that range delta, your wave function does not change much. I assume the wave function does not change much so assume that wave function is unchanged in the interval which is a by 2. This within 2 delta, it doesn't really change. And I then pick the value of the wave function at the midpoint. What is the midpoint? Anish, what is the midpoint?
A by 2.
Yeah, so 2 by A minus V naught, these are constant come out. And also I put x equal to A by 2. So it will be sine square pi into A by 2 divided by A. And then I have integral dx. What is the integration? If I integrate, what will be the answer to this?
2 delta.
So it will give you 2 by a minus v naught. Now sine square pi a by 2 is what? Sine square pi by 2.
Yes, sir.
1.
Okay, which is sine 90 is 1. So and
One.
this integral will give you what? How much it will give you? 2 delta, no? It will give me 2 delta,
Yes,
no?
2 delta.
So this is the answer. This is exactly the answer. Okay, this is exactly the answer. So I can just, if you want, this is minus 4 v naught delta by a. Of course, you can see this correction is very small because delta is very small usually. This is the first order correction to the ground state energy of the particle in a box problem. Okay, what will be the first order correction to, if you have the same setup, if I ask you to calculate the first order correction to the next excited state, like psi E2, E21, what is the value? Can you calculate?
Psi 1 will be changed to Psi 2 and then the process will be similar.
Yeah, but can you tell me what is that? You can tell me the answer, even without doing the math.
0.
Yeah, why 0?
Sine pi.
The sine square 2 pi a by
Because if I follow the same procedure, and if I say the integral is dominated by the wave function's value at x equal to a by 2, what is that value? It is
0.
0. Okay, so this is going to be 0. You can check yourself. This is an example of your perturbation. So what should I do next? Now I should move and look at first order correction to the wave function. Say that. So let us try to do it. The first order correction to the wave function. In general, correction to the wave function. Now you remember from your, I think, introductory classes that if I solve an eigenvalue problem, I know all the eigenfunctions. Then these eigenfunctions, they form what is known as a complete set. How many of you remember a complete set? If I have if I have a Hermitian operator, if I solve the eigenvalue equation for that Hermitian operator, then the eigenvalues which I get, they form a complete set. What does it mean? What does it mean?
Any wave function in the space can be expanded.
So any arbitrary wave function, so any psi x, I can express as a linear combination of, say, this wave function. Any. So if this is true, then if this is true, then what can I do? I can say this psi n1, this is the first order correction to the, this is the first order correction to the wave function for the nth eigenstate. So the nth so this one, ideally one should be able to write it as a linear combination of what? All the unperturbed Hamiltonian wave function like this.
Yes, sir.
You get it? This is very important. And see, this is so beautiful because you know this postulate of quantum mechanics, the consequence of, it is a property of the Hermitian operator, what the H is, Hamiltonian is. You have these eigenfunctions and they are exactly they form a complete set, and then as a result what happens that when you take a linear combination of them, you can express any arbitrary wave function. So in principle, the first order correction can also be expressed as a linear combination. Can I write it down using the summation sign? Sigma m is equal to 0 to infinity. M is not mass, this is the index. Cm psi m 0. This is quite nice, isn't it? Because you know all the psi m's 0. You know psi 1 0, psi 2 0, all these things you know. But if I now ask you to do that psi n, this is fine. Now, if I ask you to calculate for the say n plus 1 state, what will be the answer? First order correction to the n plus 1 state. Anish or any other can answer. Anyone can answer.
The CM coefficients will be different.
It will be the same structure, only the coefficient will be different, isn't it? But I'm not complicating my notation, because this Cm would also depend on which state you're talking to, which state. So Cm would be an unique set. If it is psi n, then you have one unique set of Cm. If it is psi n plus 1, you'll have another unique set of Cm. This coefficient will change. You have to mix these wave functions in a different proportion in order to get that wave function, because that wave function is different, isn't it? Okay, so now you recall what the equation I had. We had this equation. Let us write it here. What are the equation? Because this equation is very useful. H 0 psi n 1 minus en 0 psi n 1, that is equal to en 1 psi n 0 minus h 1 psi n 0. We had it, no? I'm just writing it again. Is this fine? Please say yes, because there is nothing
Yes, sir.
very difficult. So what should I do now? I take this guy psi n 0, sorry, psi n 1, and substitute back here. So what will be the first term? Is this fine? Is it fine to all of you? If you have any question, let me know. Should be fine.
Yes, sir.
Should be fine. Now what will be the first term? You know that when h0 operates on psi 0, what should I get? This is number, doesn't matter, no? First term will give me em0, and this is what you should have. This is fine? This first term, because h0 operating on psi m0 will give you em0 times psi m0. em0 is constant. It's a number. I can take it outside the sum. It's clear?
But sir, EM is different for every M, right?
Yes, sir. So it should be within the summation.
Yeah, sorry. I cannot take it outside here. But yeah, but I can. Sorry, this is a problem with. Yeah, but I can. Problem with your. Just wait. This is somewhere here. And then I have this term. Okay, I'm not writing all the terms. I'm lazy, I'm not writing. Now what I now do, I just multiply with psi L star 0 and integrate. Multiply with this and integrate. If I multiply the psi L star 0 and integrate, what should I get? What should I get? The first term. The first term is, of course, you have integral d tau. You have psi L 0 star, which you have multiplied from the left hand side. What will the first term? em0 and see and then en0. So you have em0 minus en0, isn't it? So it will be like m0 to infinity cm em0 minus en0. This is fine.
So, sir,
And then you have im0.
here
Yeah,
all the term will become 0 except 1, right?
we'll see. But this is fine. This is fine, no? A0, because this will give me em0 and you have en0 here. So I can say em0 minus en0 like this. What will be the next term? If I take on the other hand, right hand side, d tau psi L0 star. What is this term?
Sir,
Can you hear me now? Some problem with the internet.
Yes, sir.
And can you see the slide now?
yes, sir.
Yes, sir.
Okay. So we had these terms and somebody asked a question that, okay, sir, one term will survive, and that is true. So unless m is equal to L, the above integral is 0, isn't it? Look at it carefully. Why it is so? Because the psi L, psi m 0, they form an orthonormal set. These are constant, no? I can take the sum outside because this is what? The term on the left hand side. So in order to know that the internal is on, sometimes you say yes, yes. Are you there?
Yes, sir.
Yes.
Yes, sir.
So I can write like this, no? This is the integral. And obviously this term is 0 when L is not equal to M because they form an orthonormal set. So only when M equal to L, this term is non-zero. Is this fine?
Yes, sir.
Now if I go back, now if I write down like this, basically then what I have here is this, like this. Okay. Sorry, I have to wait for a minute, maybe some problem with. Some problem with okay. So what I had here was this one. So only M equal to L will survive. So you'll have only one term from here, isn't it? Only M equal to L. You'll have CL EL0 minus EM0 is equal to En1 d tau, then psi L star 0 psi n 0 minus this d tau.
Sir, it should also be 0, right? Why are we writing
Which one should be
first
0?
term?
Why? Yes, yes, yes. L equal to only when L M equal to L, then only it will be so unless M equal to L, the above integral is 0, isn't it? What is that? Unless M equal to L, M equal to L, the above integral is 0. So it should be L minus En, no? This should be N. Here N, isn't it?
Yes, sir.
Yes. Yeah, so there is a typo.
Sir, I
This-
was talking
Yes.
about the first term after equal to sign.
Yes, yes, yes. I'll just, of course, just wait. There's a problem with this eraser and I cannot write It has become so difficult. Yeah, so this term, what he is saying, that now this is, now you have to understand one more thing. Now this is psi L. What is the term? Slides are not moving. How can I proceed? Because I just want one more minute, 5 more minutes maybe. Okay. So we had like psi L0 star psi N0. Now m equals to L, the above integral is 0. So here what you are saying, that psi L0 star in psi N0, yeah, this term is going to be 0. Yes, obviously. We'll see that. Let me write it down here properly. I even select. Now this is fine. I think this is the expression. What I had was the expression, and then of course this term is going to be 0. Then what I have CL equals to what? Can anyone tell me? CL equals to minus, you have integral d tau psi L 0 star H1 psi N 0 divided by EL 0 minus EN 0. Are you guys there? Is it fine?
Yes, sir.
Now if I take L equal to N, what will happen?
Average value will come above.
If I take
Then
L
EN will
equal
be
to
0.
N, L equal to
En
N.
will come. En.
Yes. If we take in this equation, then this term will be NN. This will be 1, not 0. So this will give you EN 1. And that is equal to be this, because this is 0. This will be d tau. And this you know already, because we have done it. We have done this, isn't it? Earlier. First order correction to energy. Okay? That's fine. And now what I'm going to do, I'm going to use a shorthand notation for this. I will stop here. Let it be there. So, okay. So psi n, the first order correction to wave function is going to be m 0 to infinity. Obviously, but you have to understand that L is not equal to n. It's not m, this is L, because I have changed this. This is a problem actually. L equal to 0, because this is CL. I have a minus sign here, minus. Then I have this integral, isn't it? I'll write the integral. I will stop here today. What is that integral? Now this integral, I can use some shorthand notation for this. I think you have been introduced to this kind of notation. This one I am writing it as H1, but not with the hat, but Ln. This is a matrix element. This is fine with all of you?
Yes.
Hello? This is fine?
Yes.
So if I take this, I put it there, so it will be H. I don't need to put hat because it's a matrix element itself. Ln Of course, this is for 1. And this is, and then what I should have? I should have psi L 0. So, and if I multiply this with lambda, this will give me first order correction. So this will be like this. Is this clear to all of you? And this is how it is. This is nothing but, if I use the Dirac notation, it is psi L 0 H 1 psi n 0. This is how it is. So we'll stop here. So we have now calculated the first order correction to the wave function. We start from here. Okay, and we proceed and do some example. Hopefully by Friday we'll finish perturbation theory, and then next week we'll talk about variation theory, which is very important. So with that, I will stop presenting.
So I have a question, if you don't mind.
Yes, please.
So on the very last slide, when you said that if L is equal to N, the energy expression is that, how did you compute that from the equation at the top? Were you just saying that it is from what we know from
This one. Okay, if L equals to N, what will happen to this integral? This is psi L, psi n, no? Psi star n, psi star n. What is that?
Okay, right.
This is 1.
Yeah.
I did not write it. And this is 0.
The last integral.
Yeah, this one is 0. En minus En is 0. No? En 0 minus En 0 is 0.
Okay, fine.
This one is 1. 1 times En1. And this will remain. So En1 is going to be equal to this. Isn't it?
Okay.
I just get the
Right.
first order correction to
Fine.
the energy. Yeah.
There was another question related to this
Yes.
concept only. So someone at the initial parts mentioned that the inner product between psi 0, psi n 0, the zeroth order nth eigenfunction, and some psi n I, 1 or 2, that should be 0.
No.
So
No. It is not true. It is not true. It is not true.
I mean,
There is no,
what
because
is the-
because it is not true, because they belong to different Hamiltonian. No? If you have wave function belonging to the same Hamiltonian eigenfunctions, they are orthogonal. But psi n 0 means 0 order, and psi say m1 means first order. They belong to different Hamiltonian, isn't it?
yes, sir.
So there is no guarantee they will be orthonormal.
Yes, sir,
Yeah,
but-
that I definitely understand that there's no guarantee. But the question that a follow-up question could be that what is the normalization you are taking for this this approximate wave function psi, which is like psi 0 plus lambda times psi n1.
Yeah,
plus-
so now this is the correction, no? So you have to normalize it. So each normalization is what? Psi n star, psi n integral should be equal to 1. So I have to, this is your psi n1, no? If I don't have the lambda. So I have to multiply it with its complex conjugate and integrate over the all space, and that should be equal to 1. That is the normalization condition.
so the normalization condition would be the total psi, like the inner product.
No, each.
Psi get psi.
No. So I am doing it for psi 0. I am doing it for psi n. Okay. And of course, end of the day, when you have the new wave function, if you truncate after first order correction, okay, that you can also normalize.
But that will have to actually like figure out the normalization constant again, because this won't return the normalized.
Yes. So there is no guarantee. Yeah, I understand. So there is no guarantee that I know, because then you have the cross terms. What you are talking about? Psi n0 and psi n1. This kind of cross terms, isn't it? So we don't talk about normalization there. We'll talk about it later. Okay. I know your question is how to normalize the total wave function, isn't it? That is your question, which is your psi 0
So,
plus first order correction or some other corrections.
I actually can understand it in two steps. So the one is you assume an intermediate normalization where you actually say that the total wave function inner product with the zeroth order wave function, the known wave eigenfunctions, that is normalized. If you start with that prescription, you'll have those particular things orthonormal, which are orthogonal in fact. which are psi n 0 and psi n I. Because psi n 0 and psi n 0 will be 1, and the total wave function in psi n 0 is 1. So if you expand, all the other inner products will go to 0. And then you'll have the very same picture. I mean, the cancellations we made and all. And
Yes.
there we expanded psi n I, psi n 1 to in a basis of the
Yes.
eigenfunctions.
Yes.
We will naturally exclude the L equal to L part, because otherwise you won't have the 0 inner product.
Yes,
Naturally, we won't.
but there is no guarantee. Is there a guarantee that your
No, after that there is, yeah.
after that there
Assuming
is,
that,
but you have to assume that, no? You have to assume that at the beginning.
yeah.
You
And
have to
after that
assume,
we can
of course,
renormalize to
of course,
the total
of course,
psi
of course.
inner psi.
You have to assume something, otherwise you cannot calculate the cross terms between the zero order and the first order wave function.
Yeah.
That you have to assume, of course. But here you have not assumed so far, because they are not bothered about the normalization of the total wave function. You are just looking at the total, looking at the correction to the wave function. Okay. So usually what happens that you can calculate these corrections, and then you'll have a new function. And then you normalize that new function just by integrating over all space.
Right, and we have already expressed that in terms of known functions. So
Yes, like that. Anyways, so we'll talk about it in the next class, and I think I'll now stop presenting, and I'll stop recording as well.